The first goal of today is to prove a theorem which says that geodesics are locally minimizing. And in order to do this, I need to introduce the definition of uniformly normal neighborhood. So suppose that Mg is a Riemannian manifold. Then a subset W of M is a uniformly normal if there exists some positive number delta such that W is contained in a geodesic ball of radius delta around each of its points. Please pay attention to the word each. If delta is any such number, then we say that W is uniformly delta normal. The first result I want to prove is an auxiliary lemma. Uniformly normal neighborhood lemma, which says that given a point P of M and any neighborhood U of P, there exists a uniformly normal neighborhood of P contained in U. How to prove this lemma? Suppose that u0 x1 x2 xn. This is a normal coordinate chart centered at P, with u0 contained in U. Suppose that x1, x2, xn, v1, v2, vn are the coordinates for the subset of the tangent bundle given by pi inverse u0, where pi is a projection sending Tm onto M. Okay, let's observe that we can identify u0 with an open subset of Rn because of these coordinates. And we can identify Tm with the product u0 times Rn. Now let's give a look at the exponential map. So the exponential map for u0g is defined on the open subset E which is contained in u0 times Rn. Then we define the map capital E from E into u0 times u0, writing E of xv equal x exponential map at x evaluated as v. This map has an invertible differential at the point p0, differential of E at p0. This is represented by the matrix dxi, dxj, dvi, dxi, dvj, delta x I, delta xj, delta x I delta Vj. And it is clear that this matrix has the following block structure, where the first block on the top and on the left is identity. The same is true for the bottom, the block at the extreme right and the bottom. Instead, the remaining blocks are respectively 0 and something that I will denote by a star, but this is not important because we know that a matrix having this structure is invertible. So the inverse function theorem implies that there exists a neighborhood U contained in U0 times Rn of P0 and V contained in U0 times U0 of PP such that E is a diffeomorphism from U to V. Now we can make these neighborhoods smaller and assume that U is a set of the form W times B epsilon 0, where W is a neighborhood of B and B epsilon 0. This is above in the V coordinates. So this has the following consequence. For each x in W, exp, the exponential map at x acting on B epsilon 0, this is nu x, where nu x is a set of points denoted by y, such that x, y belongs to V. And it is easy to see that this map is a diffeomorphism. It is clear that it is smooth. Instead, its inverse is given by this formula, pi 2 composed with the inverse of x, y, where pi 2 is simply the projection from U0 times Rn onto Rn. The reason why this is true is that this map was defined as the map sending xv on exp and image by the exponential map of v. So when you write this way, what you get a pair x in the vector, but you want only the vector, so you compose with the projection the first factor. Now, if necessary, we can make W even smaller until, so shrink W so that you have that this inequality is true. Where C and capital C are positive constant. So this says that for each x in W, then B epsilon 0 contains a gx ball of radius at least epsilon over c. So this follows from this inequality here. So if you set delta equal epsilon over c, we have proved that for each x in W, there exists a G geodesic ball that is a geodesic ball with respect to this metric, of radius delta and centered at x. So now we have to prove that we have a uniformly normal neighborhood. The candidate, the subset which is candidate to be a uniformly normal neighborhood is W, because we proved that for each x in W there is a geodesic ball of radius delta centered at x. What we want to prove is that W is contained in this kind of geodesic balls. So the idea is that you shrink W if necessary, so that the diameter of W is smaller than delta. So this says that W is contained in a metric ball of radius delta centered at x, and now we use a corollary which says that metric balls and geodesic balls coincide. So W is contained in geodesic balls of radius delta centered at x. We know that this ball exists because we proved it before, and from the fact that x is arbitrary, we have that W is the uniformly normal neighborhood we are looking for. And this is the end of the proof. And now, as announced, we prove the theorem which says that every geodesic is locally minimizing. So suppose that gamma is a geodesic curve in M. We can suppose that I is an open interval up to considering an extension, and fix T0 in I. Now suppose that W is a uniformly normal neighborhood of the point gamma T0. This neighborhood exists because of the auxiliary lemma we proved 1 minute ago. And let I0 the subset of I such that T0 belongs to I0, and gamma of I0 is contained in W. So if A and B belongs to I0, with A is more than B, Then gamma B is contained in a geodesic ball centered at gamma A. The reason why this is true is that gamma B belongs to W. W is uniformly normal, so W is contained in a geodesic ball centered at an arbitrary chosen point of W, so for example gamma A. So this is true. Now what happens if we work inside the uniformly normal neighbor W? The answer is look at what proposition 6.11 says. That is, I recall the proposition. Suppose P in M, Riemannian manifold, and Q belongs to geodesic ball centered at P. Then up to a reparametrization, the radial geodesic from P to Q is the unique minimizing curve in M from P to Q. We want to use this proposition with P equal gamma A and Q equal gamma B. So what we get? We get that the radial geodesic from gamma A to gamma B is the unique minimizing curve from gamma A to gamma B. But the restriction gamma restricted to AV, this is also a geodesic joining gamma A to gamma B, lying in the same geodesic ball. So this geodesic must coincide with this geodesic here, and consequently it is minimizing. And this is the end of the proof. Using the argument of this proof, you can give an alternative proof of a theorem, precisely theorem 6.4, which says that every minimizing curve is a geodesic if parameterized by Ackland. I will leave the details to you. What I want to do now is to introduce the definition of injectivity radius that will be useful in the sequel. So suppose that we have a Riemannian manifold without boundary. Then for each P in M, we define the injectivity radius of M at P as follows. The notation we use is this one. This is the supremum on A positive such that exp the exponential map from BA 0 So I was saying this is supremum of all positive numbers A, such that the exponential map from this ball onto its image is a diffeomorphism. So if there is no upper bound, then the injectivity radius is infinity. And we can also define the injectivity radius of M. In this case, we don't make any reference to the point. as the infimum of the injectivity radius is at P, with P varying in M. This number can be 0, can be positive, or can be plus infinity. It is easy to prove that if Mg is a Riemannian manifold which is compact, then its injectivity radius is positive. For each x in M, there exists delta x positive such that x is contained in a uniformly delta x normal neighborhood Wx. And injectivity radius at x prime larger or equal to delta x for each x in W. Sorry, x prime in W. Now, since M is compact, then M can be covered with finitely many of these neighborhoods, and this implies that the injectivity radius of M is larger or equal than the minimum of delta x1 delta xn. This number it is clearly positive. It remains to understand why it is finite. This is finite because a compact metric space is bounded, and a geodesic ball already C contains points whose distances from the center are arbitrarily close to C. The next important definition I will introduce today is the definition of completeness. We already know what is the meaning of metrically complete space. This means that it is a complete metric space, but we have also geodesically complete spaces, and this means that every maximal geodesic is defined on R. What we want to show is that these two notions are equivalent. This is what the Hopf-Riemann theorem says. In order to prove this theorem, I need the technical lemma, which says that if Mg is a connected Riemannian manifold, then if there exists P in M such that the exponential map is defined on the whole TPM, then we have A given Q in M, there exists a minimizing geodesic segment from P to Q, and B, M is metrically complete. Okay, let's prove the lemma. This proof is quite long, so let Q in M be an arbitrary point. We say that if gamma is a geodesic segment starting at P, then gamma aims at Q if 1 gamma is minimizing and 2 the distance from P to Q is equal to the distance from P to gamma B plus the distance from gamma B to Q. Unfortunately, I have to erase. Now, in order to prove A, we have to prove that there exists a geodesic segment such that gamma A is P, it aims at Q, and the length of gamma is exactly the distance from P to Q. Why this is true? Because if this geodesic segment aims at Q, then it is minimizing, and this combined with this identity proves that there exists a minimizing geodesic segment from P to Q. In fact, if we use this identity here and this one, we get distance from P to Q. This is the distance from P to Q because gamma B coincides with Q, plus distance of gamma B Q, which implies that gamma B is equal to Q. Oops. Okay, choose epsilon positive such that there exists a closed geodesic ball centered at P such that Q does not belong to this ball. Since the distance function is continuous, then we can say that there exists a point X in S epsilon P, so this belongs to the geodesic sphere, such that the distance from X to Q attains its minimum. On S epsilon P. So if you want to make a picture to understand this fact, this is P, this is Q, this is the geodesic sphere S epsilon P. What I'm doing here is that there exists a point X such that the distance between X and Q is a minimum. So let gamma be the maximum unit speed geodesic such that gamma restricted to 0 epsilon. This is the radial geodesic from P to X. By assumption, gamma is defined on R. We show that gamma restricted to 0 epsilon aims at Q. We know that this is minimizing, and the reason is that we are working inside a geodesic ball, so you can use the proposition 6.11. So now we need only to show that dGPQ is a distance dx plus dgxq. In order to prove this, we consider sigma from A0 to B0, sorry, from A0, B0 to M, and we suppose to be an admissible curve from P to Q. Suppose that T0 is a point in A0, B0, such that sigma T0 belongs to S epsilon P for first time. So this means that this is sigma T0. So we call sigma 1 equals sigma restricted to A0, P0, and sigma 2 the restriction to T0B. So this is sigma 1 and this is the image of sigma 2. It is clear from the picture that the length of sigma 1, this is larger or equal than the distance from P to sigma T0, which is also the distance from P to X. Instead, what about the length of sigma 2? The length of sigma 2 is clearly larger or equal than the distance between sigma T0 and Q, which is larger or equal than the distance from X to Q. Then if we sum, we get that the length of sigma, which is the length of sigma 1 plus the length of sigma 2, this is larger or equal than the sum of these two distances. And now we take the infimum on sigma, and we get that the distance between P and Q is larger or equal than the right hand side of this inequality. We want to prove that the identity holds, and we have just to combine this identity with the triangle inequality, and we get this one. So what do we do? What we did so far is that this curve here aims at Q. Second part, suppose that T is the distance between P and Q. We define A as B in 0T, such that the restriction to 0B aims at Q. We know that epsilon belongs to A because this aims at Q. We define A to be the supremum of A. Clearly this is larger or equal to epsilon. And we can observe that this is closed in 0T by continuity of the distance function. This implies that A is not the supremum but is a maximum, so this belongs to A. What we want to do is the following. Go show that A is equal to T. If this is true, then this is a geodesic having length equal to T equal to distance from P to Q that aims at Q. And this is the end of the proof of part A of the lemma, because this curve is a geodesic which is minimizing and joins P to Q. So we argue by contradiction, and we suppose that A is smaller than T. So set y equal gamma A, choose delta positive such that there exists closed geodesic ball centered at y such that Q does not belong to B delta bar y. So if this is P, this is gamma T, this is gamma A, this is delta, and Q is here. So if A belongs to A, we have that the distance between y and q, this can be computed as the distance from P to Q minus the distance from P to Y. And clearly this is equal to T minus A. Let Z to be a point in this geodesic sphere where the distance between Z and Q attains the minimum, So for example, this point so denote by tau the unit speed radial geodesic from Y to Z. You can use the argument applied to gamma restricted to 0 epsilon for proving that tau aims at Q. This fact implies that this distance it is equal to this difference and this is equal to T minus A minus delta this follows from here now we use a triangle inequality and the proposition and this formula, sorry, to get that the distance from P to Z can be estimated this way. We have almost finished it. Fortunately, I have the raise. Now, the curve that you get considering this one followed by tau is minimizing from P to Z. Because the distance between P to Z is A plus delta, and the length of this curve is A, the length of tau is delta. So this curve is the good length. If this is true, then there are no corners, And this implies that Z belongs to gamma. So Z is not here, but here. And if this is true, then Z is a gamma of A plus delta. And then, what is the distance between P and Q? This is dgpz plus dgzq. This is A plus delta. Sorry, I'm using I have to use another formula, otherwise we don't understand what we are doing. I have to recall this formula here, dgzq this is T minus A minus delta. I unfortunately erased this formula. And as a consequence of this formula, we get that the distance from P to Q, which is T, it is equal to A plus delta plus the distance from Z to Q it follows from here. Replacing T by dgpq. But this is also dgpz plus dgzq. And this is equivalent to say that gamma restricted to 0A plus delta aims at Q, and A plus delta belongs to this A here. Contradiction? Because A was the supremum of this set. Instead, here we are saying that A plus delta with delta positive belongs to A. So this is the end of the proof of the first part of the lemma. Now we have to prove that the manifold is metrically complete. That is, every Cauchy sequence in M converges. So suppose that this is a Cauchy sequence in M, and we define gamma Ti as the exponential map acting on TVI. So this is a unit speed minimizing geodesic from P to Qi. We define Di to be the distance from P to Qi, so that Qi is the exponential map of acting on Di Vi. Let's observe two things. This is bounded in R because Cauchy sequences in a metric space are bounded, and this one is a sequence of unit vectors in TPM. Implies Di Vi, this is bounded in TPM, implies there exists a subsequence Dik Vik, which converges to V in TPM. Since the exponential map is continuous, so by continuity, Qik given by the exponential map acting on Dik Vik these will converge to the exponential map acting on V, and since this sequence is a Cauchy sequence, then they converge to the same limit, and this is the end of the proof. Let's stop here. Thank you.